The rivers with a sediment load have reached the sea. Here, they will enter a very dynamic environment with bathymetries varying from 0 to more than 10,000 meters. A domain characterized by slow and very rapid water movements, a region where life can be abundant or nearly completely absent. We will look at all these features in the coming slides, always with the overarching goal of understanding the processes to increase the ability to predict the subsurface. This is the bathymetry of the seafloor along a representative transect from the coast to the deep ocean. You can see the coastal regions, the large and flat continental shelf, the relatively steep and narrow continental slope, and eventually the huge and monotonous abyssal plain. A further very important element in the marine system is the photic zone, which is the water column penetrated by light. Here, photosynthesis is possible and small plants can flourish, forming the first ring of the food chain. Underneath the photic zone, waters become dark, cold, and inhospitable. The coastal region is the area of interaction between the sea and the continent. Waves, currents, and tides can erode, transport and/or deposit sands and other sediments, resulting in a large variety of coastal types. Understanding and predicting such changes is important for geological purposes and is key for responsible management of the highly populated coastal regions. The continental shelf is a flat domain adjacent to the coast, characterized by water depths below 150 to 100 meters. A well-defined shelf edge marks the transition with the continental slope. The width of the shelf changes from region to region and can vary from kilometers to several tens of kilometers or even hundreds of kilometers. In general, shelves associated with passive continental margins, such as the eastern side of the American continent, are much wider than those developed along active margins, such as along the Andes. Continental shelves are the domains of currents and tides and the fundamental temporary short storage place of sediments between the coast and the abyssal plain. Having passed the shelf margin, the seafloor starts to rapidly deepening, eventually leading to the abyssal plains. This is the continental slope, a tens of kilometers wide region with a slope of less than a few degrees. Nothing spectacular for our eyes of human beings, but of great importance in the marine domain. It is the region bypassed by the sediments which have been deposited on the shelf and then transported down to the abyssal plain. Huge, sediment-loaded currents move to the abyssal plain, often eroding and producing the characteristic canyons. Among many others, hydrocarbon and communication companies are very worried about these slope currents as they endanger their pipes and cables. Eventually, we reach the abyssal plains, huge regions with kilometers deep waters. Only the uppermost hundreds of meters of the water column are penetrated by light, making life possible. Below this zone, light is nearly absent and temperatures are low. A slow water movements and very little life. Welcome. We've seen in the previous clip the main morphological domains of the sea and ocean: the coastal region, the continental shelf and slope, and eventually the abyssal plain. We will look today at how water masses move in these large domains and address currents, tides, and waves. The understanding of movement of water masses is crucial for our ability to predict how sediments are eroded, transported, and deposited. This knowledge is key to answer questions such as how much sediments will we find in a specific place? Will these sediments be sand-rich or, on the opposite, predominantly shaly? At the very large scale, global currents play a key role in controlling climate, biological processes, and transporting sediments, and are responsible for many other phenomena. Currents are also active in the deep oceans, although with low speed and limited capacity to transport sediments. When currents move towards the continent, they will interact with the continental shelf and then with the coastal domain. Their movement is conditioned by seafloor topography. Water masses transported towards the coast are diverted, causing potentially very important along-shore currents, key for the erosion, transport, and sedimentation of sands. We will look in more detail at these phenomena at a later stage. A very important process controlling water movements on the shelf and around the coastal domains are tides. Tides are movements of water masses controlled by the gravitational forces exerted by the Moon and the Sun on the rotating Earth. In a graph displaying tides-related sea level changes, you see the well-known daily cyclicity driven by the attraction of the Moon and by the centrifugal force of the Earth. The diagram shows also oscillations operated at larger time scales, for instance, the 28 days monthly cyclicity. This is associated with the relative position between Moon and Earth. Tides result in major horizontal vertical movements of water. In shallow water, a small increase in sea level corresponds to a large displacement of the coastline. Consequently, large domains are regularly, twice a day, flooded and emerge again. This region is called the intertidal domain. Above this, we have the supratidal domain, which is brought on the water only at very high tides, and underneath this, the subtidal domain, which becomes submerged only at very low tides. The strength and amplitude with which the currents and tides impact the continental shelf and the coast is strongly affected by the width of the area they are flowing through. Remember this equation? We've discussed this while talking about river flow. It says that if the width of the section decreases and the discharge remains constant or even increases, then water velocity will increase and water level will become higher. The most apparent example is observed in Newfoundland, the place with the largest tides on Earth, more than 15 meters. The movement of water masses driven by currents and tide is more complex than it would look like at first sight. Water particles move very much in oscillatory movement, essentially forming ellipses which transfer energy laterally. Such oscillatory movements form waves. In the open sea, water particles are free to oscillate and will display a fairly symmetric pattern of movements. Sea waves, like all waves, have a wavelength and an amplitude. These vary a lot depending on the driving forces. Waves associated with very strong winds can have a height of up to 20 meters with wavelengths of more than 200 meters. Water oscillations decrease with depth, and at depths roughly corresponding to half of the wavelength, no movement is recorded. We can then define the wave base, which is the depth under which water is not affected by wave movements. The depth of the wave base is roughly half of the wavelength. We've seen the morphology at sea, the processes guiding the movement of water masses. We are now ready to see what happens with the sediments which are being transported by the rivers and delivered by deltas and estuaries.